Hi students, greetings of the day, and this is my 40th video of for engineering thermodynamics course, and now we are in the streamline of third unit of properties of pure substances, and the second session of the third unit is about Rankine cycle and its improvisation methods, and now we are discussing about how to improve the Rankine cycle efficiency, for which what are all the various factors which affecting the efficiency compared to Rankine cycle was studied in the last video, and now we are going to learn about one important terminology called mean temperature of heat addition, which I mentioned in my last video. Okay, right. Let me recall the concept studied in last video is even though Carnot cycle could not be executed practically, it gives more interesting inputs to us in such a way that the efficiency of the cycle could be improved either by increasing the heat addition, here that is temperature of heat addition, or by reducing the pressure or temperature of the condenser. Okay, since the efficiency is 1 minus q2 by q1, so the efficiency is purely depends upon the heat supplied, what is the temperature at which heat supplied and what is the temperature at which heat is rejected. But here in Rankine cycle, not as in Carnot cycle, instead of temperatures, that is the in constant temperature the heat is not supplied, and constant pressure, right? So constant pressure heat addition and constant pressure heat rejection takes place in a Rankine cycle. So how could we achieve or improve the existing Rankine cycle by the input given by the Carnot cycle to improve or increase the heat addition? Okay, so and also I taught you what is the difference between the heat addition process in Carnot cycle and Rankine cycle, right? Okay, now let me show in this TS diagram again that this 1 to 2 dash to 2s to 3 4s, and this is the sensible heat addition in the economizer. Okay, economizer means simply from the flue gas the heat is being supplied to the water to increase the temperature of the water, and then here exactly the latent heat of vaporization is supplied in the boiler, and again superheating takes place in the superheater tubes from that is after this vapor dome. Okay, so three sorts of or three devices are being integrated to supply the heat, which is first part is from economizer, and the second part is exactly boiler, and the third part or the improvising part of this boiler is superheating. Again it is further increasing the temperature as well at constant pressure. Okay, by getting the heat. Okay, so these three parts are equal to the line 5 6. Okay, in Carnot cycle, all the heat, it is assumed that all the heat is supplied from between this 5 to 6 at constant pressure, constant temperature. But in Rankine cycle, it is not maintained so. So what could we do? Okay, what is this term mean temperature of heat addition? Okay, so for this What you should know, no. So already I told you T2 is fixed by condenser pressure. That is purely depends upon the atmospheric pressure and atmospheric temperature. Right. You cannot reduce the condenser pressure below the atmospheric pressure. Okay. It would be usually above the atmospheric pressure, condenser pressure. Right. Condenser pressure, for which very little improvement is only possible because you cannot change the atmosphere, right? Okay. Largely or to the whole extent, the efficiency is depends upon the mean temperature of heat addition. Larger the heat addition temperature, greater the efficiency. Okay, it would be realized now that superheating of the steam will raise the value of the Tm, that is mean temperature of heat addition. What is this mean temperature of heat addition is already I told you in the last video, is nothing but when you have to find out the average temperature between this 4s to 1. Okay, and you have better what you can do is you cannot adjust this 2s to 3 line. Okay, this is fixed. Okay, you have to make the rectangle of this 1 2s 3 4s 2, the area of 6 2s 3 5. Okay, that is both the area of the Carnot cycle and the Rankine cycle should be same. In such a way, you have to change this line. This could be taken as mean temperature of heat addition in the Rankine cycle. After that is you got the full area of Rankine cycle, and now you try to draw the Carnot cycle rectangle in such a way that the area covered by the Rankine cycle and the area covered by the Carnot cycle should be equivalent. And then what you can do is, after drawing or getting this heat addition constant temperature line for Carnot cycle, that you can keep it as a mean temperature of heat addition, and according to this mean temperature of heat addition, you have to fix your superheated temperature and this economizer temperature and boiler temperature. Okay, if you both the areas have brought together equal, means then it would be so easy to find what should be the superheated temperature. Why here in the last video we didn't talk about superheat, but now I have included this superheating process. Is superheating has a very good and positive effect on not only increasing the work done by the turbine expansion, but also increasing the quality of the steam which comes out from the outlet of the turbine, so that the turbine blades, the life of and reliability of the turbine blades can be saved to great extent because of avoiding the water particles present in the steam will affect the both the quality and the material of the turbine blades. Turbine blade manufacturing and designing, manufacturing and aligning to get into the work is one of the difficult process in the power plant component design and manufacturing and even maintenance. So if you increase, that is if you use the superheat, this condition will be resulted with the great extension of the expansion process, that is change in enthalpy would be higher. That is, if you just think that now here expansion between this dry saturated point and condenser pressure is lesser than when you increase the temperature of the steam compared to, right? Okay, so superheat increases the work done by the turbine, increase the quality at the during the expansion. From here you would be getting the wet steam at this point, right? So turbine blades would be having all sort of that is problems raised by the water particles, since here the condition is wet steam. But now it is very closer to dry saturated point because of usage of this superheat. But when you are using dry saturated steam without using this, in the absence of the superheat, the final end condition of the steam would be wet steam and totally away from the dry saturated line, and also lead to erosion and other issues in turbine blades. Okay, so how you can find out this mean temperature is, after drawing the TS diagram for the Rankine cycle using a superheat. Okay, for the practical executed values or metrics, you can use it, and then you draw the Carnot cycle rectangle which is equal to the area of the Rankine cycle area, and find out the top line of heat addition, constant temperature heat addition line, and that you have it as a mean temperature of heat addition. According to that, you can fix your, that is increase your superheated temperature at the inlet, and that is pump economizer inlet temperature, everything could be changed, okay, to improve the that is not only the efficiency of the plant, but also the lifetime of the various component, especially turbine component. Okay, so this was explained here, and now a simple derivation is given for this mean temperature of heat addition is Rankine cycle heat is added reversibly at constant pressure, that you know very well, and Tm1 is a mean temperature of heat addition which is shown area under 4:1 equal to the area of 5 to 6, and then heat is added. Already what I have explained is Q1 is equal to, here you can see Q1 is equal to 4S, H1 minus H4S, right, which is equal to Tm1 into S1 minus S4S. T into ds will give you enthalpy, that is heat supplied, and then you can find out the mean temperature of heat addition by the formula of difference in enthalpy divided by difference in entropy between the condition, and fix the mean temperature of heat addition, and then from this, to get this mean temperature of heat addition, you can fix your superheated temperature. Okay. So here Rankine cycle efficiency could be Q2 1 minus Q2 by Q1, which is equal to 1 minus Q2 should be T2 into S1 minus S4S and Tm1. So directly it meant that it is purely depends upon the temperature of condenser divided by temperature of that is mean temperature of heat addition at boiler. And another one more thing, you cannot fix this two exact temperatures. Instead we are now trying to decrease the mean temperature of heat rejection and mean temperature of heat addition. Okay, that you have to keep remember. One point what we have learnt is efficiency of the Rankine cycle is purely depends upon the average or mean temperature of heat addition and heat rejection. Since heat rejection cannot be fixed by us, depends upon the atmospheric condition. Now we are concentrating on mean temperature of heat addition, because temperature cannot be fixed, but average temperatures can be achieved, okay, by some part of work.